Okay, welcome everyone, and welcome Dr. Sutrisno
Yes.
for this book. We are very happy to have you in the framework of this fellowship, London Fellowship from INI and Science Foundation. The floor is yours.
Thanks. So first, I'd like to thank you for being here. I would also like to acknowledge the institute for the funding because I received the Ramanujan Fellowship scheme. That's why I'm here. Without that fellowship, maybe I won't have a chance to visit this institute. So I traveled all the way from Indonesia. So I'm from Department of Mathematics, Diponegoro University. So it's not a very popular university. So later I will introduce my home university first for a couple of minutes. And this talk is part of my PhD project supervised by Stefan and Bayu. So I just finished my PhD around 1 year ago from Groningen, the Netherlands. And it's about mathematical theory for singular switch explicit models or singular switch dynamical systems. So it's actually a bit far from statistics and machine learning. So I'm basically a controller, so it's more related to control systems engineering, but I'm really interested in machine learning algorithms because yeah, the development of that machine learning algorithms is fascinating these days. So I'm really interested in that. That's why I'm here as well. And I can't, let's say, at least based on my feelings, I can see some prospective future works from my result, which can be applied in model-based reinforcement learning. But please don't expect too much because I'm just started learning these kind of things. So also I learned a lot from the workshop last week, and also I will learn more later in the next workshop, hopefully. And the main point here is the Well-Posedness or solvability theory. So you are familiar with the Well-Posedness of mathematical problems, of course, but we have some issues in these models. Let's see later. And it's mainly applied for constraint systems. I will give you some examples for that. And before we go into the uh, main theory, let me introduce my home university. So it's called Universitas Diponegoro. Universitas is just the university in Indonesian. The name comes from Javanese kingdom prince, Prince Diponegoro. He lived during 1700s, yes, from the Javanese kingdom, Majapahit kingdom. And this is the university, so it's very green. If you visit our main campus, it's very green, one of greenest campuses in Indonesia. And just like other universities, we have many faculties. We have also science and mathematics faculties, including statistics departments, mathematics department, and also informatics. And yeah, it's not that popular yet. The ranking is not that good yet. That's why we are trying to expand our, let's say, international collaborations and so on. And the location is in Semarang City. It's here. Maybe it's not that visible. So this is Java Island. I'm sure you are familiar with Jakarta, the capital city. Also Bali, the most popular tourism destination from Indonesia. And it's pretty close to Yogyakarta. Yogyakarta is the, I think, the second popular destination place after Bali from Indonesia. So it's pretty close to Yogyakarta. It's in the middle of Java Island. It's exactly in between Jakarta and Bali. And for the question, so most Indonesian people like spicy food. Yes. So this one is spicy meatball soup, Indonesian meatball soup. There are some other kind of meatball soup from Asia, but the Indonesian version is usually more spicy. But you can always adjust the spiciness depending on your ability to tolerate the spiciness. And we have also tofu mixed with vegetables, and this one is rice cake. We call it Winko, but the Semarang version is very special because it has coconut. And this one is spring rolls. Of course, you are familiar with that. Many other Asian countries also have spring rolls, but what makes it special from Semarang is that the filling is made of bamboo shoots, young bamboo. Yes. And for the weather, so we don't have winter there, so it's always summer the whole year. And the average temperature is around 27 to 30 degrees, but during the day it could reach around 35 degrees. So you could get sweat easily, even just from standing outside under the sun for 5 minutes or even less. And we have many interesting sites nearby to visit. So this one is Borobudur Temple, the largest Buddhist temple in the world. The French President Emmanuel Macron just visited this temple last week or 2 weeks ago. Yeah. Also, the Dutch King and Queen visited this temple 2 or 3 years ago. And we have also this volcano, which is the most one of the most active volcanoes in the world, called Merapi volcano. If you are brave enough, you could climb the mountain, and then you could reach the top of the crater, and you could see the lava inside the crater. So it's but it's very challenging, yes. And we have also Prambanan Temple, another temple. And what makes it more interesting is that there is Ramayana ballet denso. It's a traditional ballet denso. It's very nice to see. And let me know if you visit Yogyakarta or Semarang. I will take you there to see this very nice ballet dance, traditional ballet dance show. Okay, that's it for the introduction of my university, and let me bring you to the mind talk. So I will start with the motivation, and then some problems there, and also the characterizations and the role of the theory in terms of reinforcement learning. So I'm just started learning reinforcement learning, and yeah, according to my understanding, it uses learned models for state predictions. Also, it requires well-posed models. So it can use a lot of models, explicit models, I would say. So here we are talking about white box, not black box. Usually in machine learning, we use black box as the intuition, but here we are having white box. So we have an explicit model of the problem. And it uses for computing sequential decisions over time horizon, future time horizon. And because we need these well-posed models, well-posed just means we have solutions for the explicit model, and the solution is unique. So that's the basic definition of the well-posedness. We have, of course, some known explicit models already, but in this talk I would like to focus only on this kind of explicit model. So it's a dynamical system called singular linear systems, switch systems. Here K is just the time instant, X is the state or internal state of the system, and U is the inputs or the predictors, and Y is the output or the target variable. E, A, B, C, D are just matrices or parameters. But here the problems comes from the matrix E, because E here may be singular, and there is another symbol sigma for switching signal. So if the right hand side is just a linear model of the state and the input U, so the problem comes from E. So if the matrix E is invertible, then everything is fine. Yeah, because for a given X and a given U, then the future state X at K plus 1 is uniquely exists. So everything is fine. But if E is not invertible, then we could go into wrong places. I will show you more details later. And here sigma is a switching signal ruling how the system switches from one mode to another mode. So in reinforcement learning, it could be related to the environment. So when the environment of the system changes, then the parameters must change, and we need to learn a new set of parameters to keep the system working or going. And so basically the parameters E, A, B, C, D are kind of time varying, and the rule comes from the switching signal sigma. And we can also extend the study to the nonlinear version of these dynamical systems by having just F here is nonlinear, some nonlinear functions. In the literature, it's more known as difference or differential algebraic equations or descriptor systems. Here, yeah, one thing is that this is the discrete time version of the dynamical systems. Maybe most people are more familiar with the continuous time versions, where we have differential equations there, but here we have difference equation.
So you have
Yeah.
no noise? You have no noise?
No,
But
no, so far.
U is kind of could contain something like noise.
It could contain noise, but it must be measurable.
Okay.
Yes. Thanks. So on this page, showing you some, let's say, basic examples where we have that kind of dynamical system. For example, in relative economic model, we have that kind of equation as well. Also in constrained mechanical systems, electrical systems, and robotics. So what makes it, let's say, why we have singular system here is because we have these algebraic equations. So in ordinary system, we only have this, let's say, differential equation, ordinary differential equations. But once we have an algebraic equation here, and then if we couple these two equations, then we will end up in that kind of singular systems or descriptor systems. But yeah, most of the applications are in mechanical systems or control systems engineering. And that's why it's usually called systems with constraints. So it's very prospective in the applications because usually mechanical systems have constraints. Okay, on this page, I want you to focus on this switching signal. So the switching signal sigma is just a function mapping from the time steps to the mode. So let's say the system starts with some mode, sigma 0, for example, which is active from the time step 0 up to case 1 minus 1, and then it switches to another mode, sigma 1, and so on. But of course, we could also switch at every time step. So in that case, we are having time varying systems. Okay, and yeah.
Do you know sigma or p in advance?
Sigma of the switching signal?
P.
Which one?
The number of states.
Oh, here.
Yeah.
The set of modes, the number of modes. Yes, if we want to have the it's also related to the solvability notion I will introduce you later. So if we have a finite set of modes, then yes, we have P here. But if not, then we could still use the theory later. But in that case, we have a fully time varying systems. So that means we could switch to an unknown mode, but the my theory later still works in that case, for that case as well. Yes, but for this study, we can assume that we know the set of modes already.
Okay.
Yeah.
And the second related question is, do you know sigma, or do you have to learn sigma as well?
Yeah, the same for sigma. So depending on our situation we are having in the problem. So if sigma, the switching signal, is known a priori, we know the switching signal already, then it will be better. But it's also fine if we don't know the sigma in advance. In that case, we need to have well-posedness for every switching signal, for any possible switching signal. Yeah, because if we don't know the switching signal in advance, then the system could switch to some unknown mode, and then in that case we need to we need to make sure that the system is well posed for any arbitrary switching signal. Yes.
And final question, why is it problematic to have the matrix E which is not invertible? If you have infinitely many possible solutions to this equation, because
yes, true.
Is it a problem or not? Or can you give us some intuition for justifying this problem?
Yes. So here, so the matrix E comes from the coupling of these two equations. But what's the problem here? So imagine, I think I have the, so here, yes, actually I explained that problem here. So imagine you have, for this equation, we only have one mode 0, and also just one time step from the initial time step 0 to time step 1. And by only just looking at this equation, we already could have a problem. So this is just a system of linear equations. So well-posedness means for any given x0 initial starting point, let's say, we have to have a unique x1. But because in general E0 is not invertible, so assuming that E0 is not invertible, then we have this problem. So x1, we only can conclude this one. So x1 must be some vectors in this set or affine subspace, kernel E0 plus some vectors here. If x0 is given, then this is just a vector. E0 plus here is the pseudo inverse, generalized inverse. If E0 is invertible, then this is fine. X1 is unique, yeah, exists and also unique for a given x0. But if kernel E0 is not just a zero matrix, then of course x0 is not unique. This is the problem, the main problem. So if x1 is not unique, then the system could go widely to somewhere else without our intention, right? For a given x0 starting point.
Unless you penalize by the norm
yes.
x1.
Yes, of course, yes. That's why we need the well-posedness. So later I have a condition in which the system is well-posed. Yes. Also, if E0 is invertible, then if A0 is invertible, but A0 minus 1 here is just the inverse if A0 is invertible. But if it is not invertible, then A0 minus 1 is just the pre-image. So if E0, this one is invertible, then this is just the whole space. So we can start from any initial position or point. But if this is not the whole space, then we cannot start from any position or any initial states. So this one is called the consistency space of the system. So the system must start from this subspace. So we have these two problems. So first, we have some inconsistent initial values, initial positions, and also in general we have non-uniqueness. And later I will show you the condition such that we have the uniqueness. And there is also another issue called non-causality, but maybe I won't go into details on this. So non-causality means the current state or current solution depends on future information. But in this study, I want to have causality, which means that our current state depends on past information. But of course, we could use prediction to predict the future informations. But in that case, we will end up in a different solvability letter. So that's one of my future works. If we want to drop this causality requirement, then and we only want to have these two properties, then maybe we could end up in a different situation. And to cover these three properties, so I want to have a well-posedness or solvability notion, which is causal. Yeah, causality could also means causal with respect to states, inputs, also swing signals, but I won't go into detail on this. But at least we need to have extended uniqueness of solutions. Also, there is another thing here. This is more like the implication, but apparently it's B implication. So if the system is well posed, then later there exists a surrogate system. What is that? I will introduce you later. So in order to have these 5 properties, I use this solvability notion. So here, the system is solvable if and only if for any arbitrary time intervals and for any initial condition from the consistency space, and for all switching signals, and also for any input sequences, then we have a unique solution on the time interval. In this way, we can have those 5 properties. And yeah, here S is the consistency space, but the one I showed you earlier is for the homogeneous case without P or without input U, but here we have the input U and also the matrix P, but the definition is the same. So this is the condition, the necessary and sufficient condition. So this will be solvable if only if this inclusion holds for any ing in the set of modes. So here we have that we know a priori it happens the set of modes. We know the modes already, and but here we have direct sum. So direct sum means that first we need to have that the intersection between these two subspaces is just the 0 factor, and the second we need to have this inclusion. So if this inclusion holds, then we have that the system is well posed. And if the system is well posed, then we can find an ordinary system. So we can somehow convert the original singular system into this ordinary system. So this is just so phi and theta here are just some matrices calculated from E, A, and some other informations, but maybe I won't go into detail on that. But let's just consider this, and this are just some matrices. So every solution of the original singular system is also a solution of this ordinary system. So this is called the surrogate system of the original singular system. But maybe some people won't agree with that term, surrogate system, because many other people use the term surrogate as some other things. I saw that term as well during the workshop last week. Okay, so let's call the condition number 1 here is jointly strictly index 1. Okay, for the system. Actually index 1 means something, but I think it's too far. So the whole picture is like this, but let's just focus on this. So the theorem I showed you on the previous slide is just this part. So the system is well posed if for all switching signals, if only if the condition number 1 on the previous slide is satisfied, or it is jointly strictly index 1. But if we drop the solvability or well-posedness for all switching signals, we just requiring the well-posedness for a fixed mode sequence, but with arbitrary switching times. So in that case, we have a mode sequence. So we know to which mode we are switching, but we don't know the switching times. We don't know when we are switching. So in that case, we need solvability or well-posedness for a fixed mode, a given mode mode sequence, but with arbitrary switching times. And of course, this one implies this. And we have also another characterization. So we can relax the joint index one condition number one to some more relaxed condition. And also, if we know the switching signal in advance, we know the mode sequence, we also know when we are switching. So that means that we are working only on a very specific switching signal. Then we can relax the condition as well as just some more relaxed condition. And one thing that is interesting is that well-posedness for a given switching signal, we know when we are switching and we know the switching sequence, does not imply solvability or well-posedness for mode sequence and also for all switching signals. So that means that we could have a system which is well-posed for a fixed switching signal, but it's not well-posed if we don't know the switching times or even arbitrary switching signals. I have an example for that as well. And we also have some other solvability notions, but it's too much, I think, so we could just focus on these green things. Okay, if you are interested to read more, then you could check my PhD thesis to see these whole things. Okay, so this is the example of one interesting observation as well. So if you have these two modes, two subsystems, let's say, if we are using, let's say, multi-agent interacting systems, mode 0 and mode 1, and then just by some basic algebra computation, we have these subspecies. And then for each mode I, this inclusion holds. So basically the necessary inclusion condition number one, we can use that to check the well-posedness of each mode as well. And it is satisfied. So that means that for each mode, the individual modes are solvable, well-posed. But if we switch from mode 0 to mode 1 or the other way around, this condition is not satisfied because we have some problems here. So that means the switch systems are not solvable. So this is also one interesting observation, because if we switch from one parameter to another parameter, we could end up in a non-solvable or a not well-posed switch system. So that means that we could go widely to some position without our intentions if the system changes the parameters. And the second example shows the just a solvable switch system. So this is just to show, let's say, we have some examples for that, but it's just an academic example. If you have these two modes, then the joint index one condition is satisfied for any pair ij, but because we have only two modes, then this is satisfied for 0, 1 and also 1, 0. So the switch systems are solvable, and in that case, then we could find the matrices for the surrogate system I showed you on the previous slide by just doing some basic calculations. We call those matrices as one-step maps. Yes. One more slide. So the role of well-posedness. So apart from that solution theory, the well-posedness theory, I studied as well the role of well-posedness for some other properties like reachability and controllability in control systems engineering, also observability and distinguishability. But last week during the workshop, I heard something about exchangeability in stochastic environment. I think that exchangeability in stochastic environment or in stochastic control the same or at least similar to what we call distinguishability in terms of observability or observation in control systems engineering. But I need to read more about this exchangeability property in a stochastic environment, and to see whether they are the same or one implies the other and so on. And also, of course, in model-based learning, we need this well-posedness. Otherwise, yeah, the model could or the system could go wildly to some places without our intention, and others maybe, and some potential applications through model-based learning. So we can, of course, use our explicit models, singular models, to some systems by having switching, for example, autonomous driving and so on, robotic manipulation and so on, and many more. I'm still trying to find, let's say, one potential future research direction for this application. But I have some basic result already for multi-agent based inventory systems, but I'm still working on that. And there are also this is at least from my feeling. So from the theoretical part, we could also study more about the well-posedness and also for non-linear models, of course. And this is from my feeling. So for the model-based reinforcement learning, of course, we could have switching environment, and then we could employ my solvability theory there. And also, I recently read some papers about neural networks with switching, and they employ this kind of model, singular model or descriptor dynamical systems. I'm sure it's very useful there, but of course I need to read more about that, and maybe some other open problems. Maybe you have some ideas, and I'm open to feedback, comments, especially future research directions, because I'm starting to become maybe a learner, because I'm interested in machine learning, also stochastic control problems. So maybe you could also give me some suggestions for my future research directions. Okay, thanks for your attention.